Hello everyone, I'm Professor Harrison and welcome back to our module on statistical inference. Today we're going to be covering sampling distribution and standard error. These two ideas will end up being the foundation for everything we do in inference. We're following Bess. She's an investigative journalist on a cold case she can't let go. She's been working her way through the statistical methodology behind a series of financial misconduct cases. Today she's trying to figure out if two mutual funds that have different performance ratings are actually all that different from one another. She pulls up her case file to investigate. In the last video, we established that a sample statistic is an estimate of a population parameter, and that random sampling is what makes the estimate valid. Now I want to push on something that's easy to miss. When you take a random sample and calculate a statistic, that number isn't fixed. Take the average monthly return of a fund over 36 months. If you could go back and observe a different random sample from the same population, you'd calculate a different number. Run the same fund over the prior 36 months, and the sample mean will come out differently. Run it starting 1 month earlier, and it comes out differently again. The sample mean varies from sample to sample. That's just what it means to be a statistic calculated from a random sample. So here's the key idea. The sample mean isn't just a number, it's a random variable. And like any random variable, it has a distribution. The sampling distribution of a statistic is the distribution of all the values it could take across every sample you could take of the same size from the same population. We spent a lot of time in probability module on the central limit theorem. Here's where it starts doing the work it was built for. The central limit theorem tells us that for sufficiently large samples, the sampling distribution of the mean is approximately normal. It's centered around the true population mean with a standard deviation that we can compute exactly. The standard deviation is what we call the standard error. The standard error of the sample mean equals the population standard deviation divided by the square root of the sample size. So, if individual observations have a standard deviation of sigma, and you take a random sample of n observations, your sample mean has a standard deviation of sigma divided by the square root of n. Two things worth noting right away. First, as n increases, the standard error will decrease. This means that bigger samples will produce sample means that cluster more tightly around the true population mean. That's why more data is always helpful. Not because any single observation is more reliable, but because the aggregate estimate becomes more precise. Second, the relationship is square root, not linear. To cut the standard error in half, you need 4 times as many observations. To cut it by a factor of 3, you need 9 times as many. Precision gets expensive is basically what this is telling us. Now let me be direct about a confusion that shows up constantly because it's the confusion at the center of Bess's case. The standard deviation and the standard error are measuring completely different things. The standard deviation describes how much individual returns vary around the mean. If a fund has monthly returns with a standard deviation of 3%, then individual monthly returns tend to fall within a few percentage points of the average. Some months higher and some months lower. That's volatility. It describes the spread of the underlying data. The standard error describes how much the sample mean varies across different possible samples. A standard error of 0.5% means that if we ran many different 36-month windows, the sample means we'd calculate would cluster within about half a percentage point of the true mean. That's estimation precision. It describes the reliability of our estimate. One is about the spread of the underlying data, and the other is about the precision of an estimate. They're related by the square root of n, but they're measuring fundamentally different things. If you treat them as interchangeable and use standard deviation as a measure of how reliable your estimated mean is, that's either a misunderstanding or a deception, and in Bess's case, it's the second one. Now let's go through the case. Bess is investigating a mutual fund rating agency. The agency ranks funds by their average 3-year return. That's 36 monthly observations. Ratings are assigned based on where the sample mean falls relative to other funds. The rating company then recommends the highest performing funds to people like financial advisors as funds that are worth investing in. She pulls the return data on 2 funds. Fund A has a sample mean of 1.5% per month, and Fund B has a sample mean of 1% per month. Fund A gets top tier status and Fund B gets average. To find out whether this difference is meaningful, she needs to know the standard error. Both funds show monthly return standard deviations of 3%. With 36 monthly observations, the standard error of the sample mean is 3 divided by the square root of 36. The square root of 36 is 6, so the standard error is 3 divided by 6, or 0.5% per month. Fund A's sample mean is 1.5% and Fund B's sample mean is 1%. The difference is 0.5%, which is exactly one standard error. A difference this small could easily arise from sampling variation alone. If both funds had the exact same true mean return, and you measured them over 36-month windows starting at different points in time, you'd regularly see sample means that differ by half a percentage point or more just from chance. The sampling distributions of these two estimates overlap substantially. This doesn't mean fund A isn't better, it might be, but a 3-year sample mean isn't precise enough to distinguish 1.5 from 1 based on the data alone. At least we can't tell the difference with 36 observations and a standard error of 0.5%. Bess makes this concrete for her readers. She points out that if you shifted Fund A's measurement window back by a year, you'd likely get a different sample mean, maybe 0.9%, maybe 1.8. The fund's true expected return is the population parameter. It could sit anywhere in a range centered around 1.5%. The spread of that range is determined by the standard error. The spread is real. The rating agency is treating the sample statistic as if it were the population parameter, as if 1.5% is a known fact about this fund's true performance, rather than one estimate drawn from a distribution that has a spread. Ignoring that spread is how you end up recommending funds to clients based on luck rather than skill. And Bess notes the specific version of the error in the agency's methodology. Nowhere in their rating system do they account for estimation precision. Nowhere do they compute a standard error and ask whether two funds are far enough apart to be meaningfully different. They just rank the sample means and hand the list to the advisors. The advisors likely then take the ratings at face value, sometimes investing in funds that are outperforming due to luck rather than actual skill of the fund managers. But if they wanted to know what they should truly invest in, they should look up the fund's standard deviation and calculate the standard errors to figure out whether these outperformances are meaningful. So that's sampling distributions and standard error. The sample mean is a random variable. Its sampling distribution is approximately normal. It's centered at the true population mean, and its spread is sigma over the square root of n. That spread is the standard error, and it measures estimation precision. That's a completely different thing from the standard deviation, which measures how much the underlying data varies. Larger samples produce smaller standard errors, but the relationship is based on the square root, so precision gets expensive quickly. These two ideas end up being the scaffolding for every confidence interval and hypothesis test that we will build on in this module.